Here is Newton's Laws, Part 2. This lecture will include information about weight and normal force, and what happens when an object is in an accelerating frame of reference, what happens to the normal force on the object. We'll talk about friction and the differences and similarities between static and kinetic friction for sliding solid objects. We won't consider drag force yet, which is essentially friction through a fluid. And then finally, we'll put it all together to solve problems that involve friction and inclined planes and multiple bodies. So we begin with something I've already discussed, that is how to calculate the pull of gravity on an object. This is a bit of a circular argument for now until we look at Newton's law of universal gravitation, but we're going to use the word weight to indicate the force exerted on an object by gravity, so that what we're referring to here is the kind of mysterious field force of pull of gravity on objects. It's a force that's due to an object's mass, and we can talk about it in simple terms, in terms of the pull of gravity exerted by the Earth specifically. So we're considering weight as the pull of gravity exerted by our Earth on a different object. So we're only considering Earth, or we may sort of use this model to consider other planet-type bodies. We're only functioning right now in the flat Earth approximation, where we consider the Earth's surface to be flat, where we're not far enough away from the Earth to notice the curvature of the Earth or to notice the decrease in the pull of gravity as distance from the surface of the Earth increases. So if those two things are okay, then the pull of gravity due to the mass of the Earth on another object is equal to the mass of the object we're looking at. I wish my little pointer would just point there, that m is for mass, times acceleration due to gravity. We can kind of think of this in terms of Newton's second law. This is where we get kind of a circular argument, but Newton's second law tells us that force, or net force, is equal to mass times acceleration. So if an object is in free fall, the only force on that object is the pull of gravity, so that's the F subscript g. And if the net force on an object is the pull of gravity, then we expect that object to accelerate with an acceleration equal to 9.8 meters per second squared. But we're kind of using Newton's second law to circularly argue that the acceleration is constant, is g, but we'll come to a better argument for this later. So pull of gravity of the Earth on another body is equal to that other body's mass times that constant acceleration of gravity near the surface of the Earth of approximately 9.8 meters per second squared. So we're going to use that equation then to switch between mass and pull of gravity, and then we'll use that to talk about the normal force on an object. So I've already introduced the idea of normal force. The normal force is the support force on an object that's being supported by a particular surface. The word normal doesn't mean anything about like sort of normality in our everyday parlance, but normal means perpendicular to in the math sense. So this normal force, this support force, is always perpendicular to that supporting surface. And so that is why we call it the normal force. You can always substitute support force for that word normal force. We have talked about what causes the normal force, that sort of stretching of the molecular bonds, but we are not concerned with the micro view here. We're only really concerned with the macroscopic view of the idea that the support force occurs until or unless the object is heavy enough to break the sort of bonds of the supporting surface, and then the surface no longer supports it. So we're assuming that surfaces are strong enough to support, and if that's the case, then they provide a support force that's perpendicular to the surface. If an object is at rest on a horizontal surface, then the pull of gravity on that object, so F sub g, is in balance with the upward support force of that surface. Then Newton's third law, which we mentioned in the last lecture, says that if the support surface, So if the table is providing an upward push on the object, there must then be a third law pair that the object is pushing down on the table. And so it's not the pull of gravity on the object that exerts the force on the table. It's the interaction, the Newton's third law force, between the table supporting the object and the object pushing down on the table. These two forces, red and purple, are third law action-reaction forces. It just so happens in this case that the pull of gravity is in balance with the normal force, and so all three of these vectors, the two pink and the one purple, happen to be exactly the same magnitude, and in pairs are in opposite in direction. Now for some questions. So answer the quiz questions that follow.